When an object moves in a circle, it doesn't go in a straight line, even though inertia tries to keep it that way. Instead, its direction keeps changing at every point. This constant change in direction means the object is accelerating, and from Newton's second law, acceleration implies force. That force, which pulls the object toward the center of the circle, is what we call the centripetal force. Without it, the object would simply fly off along a tangent. So, even though the speed may be constant, motion in a circle always needs a force acting inward. Centripetal literally means center-seeking. This is the force that continuously pulls the object toward the center of the circle, allowing it to maintain circular motion. It doesn't increase or decrease the object's speed, instead, it alters the direction of velocity. Importantly, centripetal force is not a new or separate force. It could be tension in a string, friction on a tire, or gravitational attraction, whatever is providing the necessary inward pull. The formula for calculating it is force equals mass times velocity squared divided by radius. This tells us that faster motion or tighter curves need stronger inward forces. Let's look at where we encounter centripetal force in real life. If you swing a stone tied to a string, the string's tension acts as the centripetal force. In planetary motion, the gravitational force between the planet and the sun keeps it in orbit. When a car takes a sharp turn, friction between the tires and the road provides the inward force. On roller coasters and loop-the-loops, the track exerts variable centripetal force throughout the ride. These examples show that although centripetal force always acts toward the center, the source of that force depends on the situation. Now comes an interesting idea: centrifugal force. If you've ever been in a turning car and felt like you were being thrown outward, you've experienced what we call centrifugal force. But here's the twist: it's not a real force. It doesn't come from any interaction, like tension or gravity. Instead, it's a pseudo-force that appears in a rotating reference frame. From inside the car, it feels real, but it actually arises due to your own inertia resisting the inward centripetal pull. So, centrifugal force is a convenient way to explain motion from a rotating perspective, but it doesn't exist in the physical sense. To avoid confusion, let's compare both forces. Centripetal force is real. It pulls the object inward and is responsible for circular motion. Centrifugal force is apparent, a reaction perceived by the object due to inertia. In an inertial frame, only centripetal force exists. But in a rotating frame, we introduce centrifugal force to account for the apparent outward effect. They're equal in magnitude but opposite in direction. However, only centripetal force has a physical origin, whether it be tension, gravity, or friction. Let's do a quick calculation. Imagine a 2-kilogram object moving in a circle of radius 2 meters at a speed of 4 meters per second. What is the required centripetal force? Using the formula force equals mass times velocity squared divided by radius, we plug in the values, 2 times 16 divided by 2. That gives us 16 Newton. So, a force of 16 Newton directed toward the center is required to keep this object in circular motion. This example highlights how speed and radius directly affect the strength of the force needed. To wrap up, uniform circular motion isn't possible without centripetal force, a real, center-directed force that continuously redirects the object's velocity. On the other hand, centrifugal force is what we feel in a rotating system, a pseudo-force created by inertia. While they appear to oppose each other, only centripetal force has real physical roots. From orbiting satellites to turning cars and thrill rides, understanding these forces helps us navigate and engineer rotating systems with greater confidence and safety.